Hello, this is Mr. Huber, and in this lesson we're going to look at multiplying and dividing radical expressions. First, we're going to look at multiplying. This is the general rule that we can follow for multiplying radical expressions. As long as the index, that's what root we're taking, is the same, then we can multiply the numbers that are inside those radical signs. Okay? So again, this has to be the same root. If this is third root and third root, we can multiply whatever the a and the b are together. That's what ab is, multiplied together. If we come down here to this first example, we have the fourth root of 20 times the third root of 15. There is nothing else you can do with this particular problem. This would just stay as it is. And you could try and simplify fourth root of 20 or third root of 15, but those don't simplify at all, so you wouldn't be able to do anything with that particular problem because they don't have the same index. This is a fourth root, and this is a third root or a cube root. So we can't do anything with that because, again, the roots aren't the same. Down here we have third root and third root. We'll actually be able to multiply these together. So if we do this here, it's going to remain the third root. Right? If you look up here, root n, and n. That hasn't changed. And we multiply the a and the b together. So now we multiply the negative 4 and 2, and we multiply those together, we're going to get negative 8. So this becomes the third root of negative 8, which, as we've seen previously, is going to be negative 2. Negative 2 times itself 3 times will give us negative 8. So that's how we can simplify that radical expression, the product there of cube root of negative 4 and cube root of 2. See a couple others here that are maybe a little more complicated and detailed. So in number 3, one other thing to notice here is we have numbers out in front of the radicals. We can multiply those together as well. So if we multiply 2 times 5, we're going to end up with 10. So 2 times 5, that's 10. And then we'd have the square root of 8 times 18 is 144. Then we have x to the 8th and y to the 5th. So when we multiply x to the 5th and x to the 3rd, we add the 5 and 3 together to get the exponent of 8. And then the y and y, this is a first power. Y to the 1st and y to the 4th. We can add those and we get the 5. So now we want to look at simplifying this radical. Let's even forget the 10s there for a moment. We simplify this radical, and when we do that, we're going to end up with 12. The square root of 144 is 12. X to the 4th. Right, remember, there's a square root. 2 would go into 8 4 whole times with nothing left over. And 2 would go into the 5 2 times, and then inside the square root sign we'd still have an extra y there. Remember, this is times the 10. Now, we don't want to forget about the 10, but we didn't need to worry about the 10 when we simplified this radical. But remember, this is 10 times this square root. So it's 10 times still all of this. So now we can multiply the 10 and the 12 together. So whatever number you might be able to take out of the radical sign multiplies this number that's in front of it. So now our final answer then is going to be 10 times 12, which is 120, x to the 4th, y squared, and then the square root of y. We look at another example here, and again we can multiply the 7 and 4 together and get 28, and then we're going to have the cube root of 250. Okay, and then we're going to have x to the 8th, y to the 6th. Extend that over a little. All right, now let's look at that square root of 250. That's going to be the part that's probably the most challenging there. So if we look at the square root of 250, that's the square root of 5 times, remember we had 5 here and 50, right? So the 5 and the 50, I can make the 50 a 5 times 10, right? 5 times 5 times 10, which is the same as 5 times 5 times 5 times 2. Okay, let's change that last one. That 2 is a little difficult to read as a 2. So times 2. Remember, this is a cube root. Cube root. So now I've got these 3 5s here. Right? 5 times itself 3 times. I'll be able to bring that outside the radical sign. So if I come back over to my original problem here, I'm going to have the 28 times. Then I'm going to bring out a 5 because I can take a 5 out of that cube root because it's 5 times 5 times 5. 3 goes into the 8 for the x to the 8th. right? X to the 8th. 3 goes into 8 2 whole times. Okay, so 2 whole times x squared. 3 goes into 6 2 whole times. Inside the radical, we're going to have this 2 still. So that'd be 2, and then x squared, because when we 3 into 8 2 whole times with 2 x's left over. Okay? And this 2 was left over inside the cube root, right, when I did the 5 times 5 times 5. And we got to remember here, I guess, to forget to bring down that cube root part. And now I can do 28 times 5. So my final answer here is going to be 140 x squared y squared cube root of 2x squared. That'd be our final answer. So we're simplifying here this radical. It's a cube root, so we got to find numbers that multiply by itself 3 times that are factors of 250. So we can kind of do that on the side if you want a little bit. That might help. And then we simplify this cube root of x to the 8th and cube root of y to the 6th the same way we would have any other time. All right? So once we get to here, we're simplifying just like we would have any other time, and just don't forget the 28 multiplies by whatever number we may be taking out of that radical sign. All right, let's check here something about a deck of cards. We have 4 suits in your deck of cards, or your standard deck of cards. You got spades, hearts, diamonds, clubs. Okay, where do these come from? How were they determined that those would be what might be used in a deck of cards? Well, it comes from the French, who settled on those 4 current suits to represent their social classes. Okay, the noble people were the spades, the hearts were the clergy, I guess they had that loving heart, the diamonds for the merchants, the workers, right? The diamonds would be kind of that currency, and then clubs representing the peasants, okay, that lower class. So those classes in their societies, and they had these symbols that represented those 4 classes. That's how they came up with those suits that would be used in our standard deck of cards. All right. Now we're going to look at quotients, dividing radicals. Okay. Again, if our indexes are the same, we're taking the same root of both a and b, then we can write this as the nth root of a over b as 1 fraction. You can separate these and write it either way. If you have it all as one radical, you can separate it as a radical of the numerator and denominator separately. If they're written separately, you can combine them and divide the a and the b inside the radical sign. So let's see how we can use this in some problems. All right, this first one is cube roots. Okay, since they're both the same index, they're both cube roots, I can work on dividing this. And so now I can divide 162 by 3. 162 divided by 3 is 54. So I'm going to, and this is going to be the cube root of 54. And then x to the 6th over x squared is going to be x to the 4th. Right, when you divide the same base, you subtract the exponents. Okay? Now the cube root of 54, I might have some work to do to simplifying that. I got to find some numbers that multiply together and give me 54, such as 27 and 2, which is useful because I know the cube root of 27. So if I can write this out as the cube root of 27 times 2 times x to the 4th. Okay. The cube root of 27, that's 3 times 3 times 3. So I can then simplify this as 3x, because the cube root goes into that x to the 4th 1 whole time, and then I'm going to be left over with the cube root of 2x. Right? This 2 stays inside the radical, and 3 goes into the 4th power 1 whole time, so x to the 1st, and there would be 1x remaining left over inside the radical sign. Right? Now let's look at this next one. And just like we saw with numbers outside the radicals when we multiplied them, we can do the same thing here with the 15 and 3. We can divide the 15 and 3. So if we do that, we'll end up with 5. And then this is a square root of 140 over 7. So 140 divided by 7 is 20. X to the 4th, y squared. Okay. 20 x to the 4th y squared. And now we can simplify that square root. So we're going to keep this 5 outside of here. It's going to be 5 times whatever we might bring outside the square root sign. So 20, if I just write it up here to make sure we know where it's coming, square root of 20 is 4 times 5. And I know the square root of 4, so that's where that's useful. That's a 2. x to the fourth. The square root of x to the fourth would be x squared, and the square root of y squared would just be y. And then I'd have the square root of 5, because I still have this 5 here left over inside the radical. Nothing left over from the x to the fourth or y squared. And so now to simplify this for my final answer, this would be 10 x squared y square root of 5. That'd be my final answer. I'd say squared there. Okay. So notice how we can simplify these. They're not much different than simplifying the square roots, cube roots, things we've done before. Now we just have to recognize there's some multiplication or division that might go along with it, you know, at the front end, and then sometimes here where we're multiplying here on the back end of that final answer. We're going to look at a couple more here just to make sure we see a few different examples. So this next one is going to bring up something that's called rationalizing a denominator. Just like we don't want to have a final fraction for an answer that can be simplified, such as something like 6 over 20, right? We could reduce that by dividing them both by 2, canceling out a factor of 2 in both of them, making 3 over 10. Okay, so we don't want to have a final answer with a radical in the denominator. So this next problem, we see the 10 and the 3. We can't divide 10 by 3. Okay, 10 over 3 isn't going to simplify. So we'll just leave our answer like that. We don't want to leave a final answer in this form. In order to rationalize the denominator, we're going to multiply by the denominator by itself. Okay, so we multiply the square root of 3x and 3x together, because in our denominator now, the square roots essentially will cancel out and we'll just have a 3x. In our numerator, this is like the multiplication problems we did before. Square root of 10 times square root of 3x would be the square root of 30x. 10 times 3 is 30, so I'd have the square root of 30x. I can't simplify the square root of 30. X by itself doesn't have a square root. Okay, so I would just leave my answer now like this. It's called rationalizing the denominator. I'm going to write another example down here below. Okay, sometimes you don't always have an x in there. Let's say I had 8 over the square root of 2. And I don't want to leave a final answer like that. So I might multiply then by the square root of 2 in the numerator and the denominator. When I do that, I'd get 8 square root of 2 for my numerator over 2. Square root of 2 times the square root of 2 cancels. And here now the 8 over 2 can be reduced to 4 square root of 2. 8 divided by 2 is 4. And I have the square root of 2. So this fraction here, if you put 8 divided by the square root of 2 in your calculator, hit enter, and you do 4 square root of 2 and hit enter, you're going to get the same long decimal answer that's on your calculator. These are equivalent to each other. We just typically don't want to have our final answer with a radical in the denominator. If we do that, it's called rationalizing the denominator. So we get a rational number in our denominator. Square root of 2 is an irrational number, if you remember back when we talked about those. Now 2 is not an irrational number, so we rationalized the denominator. And we did the same thing kind of up here. We multiplied this square root by itself. All right, if we come over here, first I'm going to rewrite this as 2 separate square roots. Okay, so I can rewrite this first as the square root of 5x and the square root of 12x to the third y. Okay, and I can actually reduce the x's here and take that away, and then this will become a 2. Okay, so now I can simplify that square root of x squared. Okay, I'm still going to have the square root of 5. I haven't done anything with that. I can't simplify square root of 5. Okay, the 12 can be a 4 times 3 because I know the square root of 4. So that's 2x and then the square root of 3y. So I simplified this denominator. 12 is 4 times 3. It took the square root of 4, which is 2. The 3 stayed inside the radical. Square root of x squared is x. Square root of y just stays the square root of y. So now I've got something that I can multiply. I don't want to just take up here and multiply by the square root of 12 x to the third y. You don't necessarily need to do that. We can simplify it first, then look at, oh, I need to rationalize the denominator. You might not have to after you simplify it. Here we do. So we're going to simplify this by multiplying by the square root of 3y in the numerator and denominator. Okay. This then is going to be the square root of 15y. 5 times 3 is 15. And then in the denominator I have 2x times 3y. Square root of 3y times the square root of 3y is just 3y. And then for my final answer now, I'm going to have the square root of 15y over 6xy, because I can multiply that 2 and 3 together to get this as my final answer. So rationalizing denominators is not always easy. It's something you want to look for at the end. If you can't simplify something and you have a radical in the denominator, you have to rationalize it. Here we worked on simplifying what we could. When we got to this point, we still had this square root of 3y in the denominator. We had to rationalize it. All right, so that's something to look at, to work on. That can be a little tricky and difficult. But remember what to do when you're multiplying, dividing, radicals. Multiply, divide them, then look at those ways we simplify them are no different than what we've been doing previously.